Welcome everyone to the 34th Flow Talk. Samuel, can you double check? I think we had 33rd last time, so 34th Flow Talk. So Flow, as you know by now, is an online seminar series in federated learning and all aspects of federated learning. You can read about all these aspects on our website. And today it is my great pleasure to introduce speaker who is a student of mine, Konstantin Mishchenko. So he's been working on all kinds of aspects of optimization and recently federated learning, distributed learning, compression, and so on and so forth, adaptive methods. And it's really a pleasure to have him speak because I'm learning as much from him as he's learning from me. How are we going to handle this? So you said you want to be interrupted during the talk, and is that how you want to handle things?
Yeah, so anyone can ask questions at any point. It's easier for me if the question is asked soon after the slide appears. And then if I don't react for something like 15 seconds to the question, feel free to interrupt me.
All right, so we'll try to unmute everybody as much as possible because we'd like to hear other voices as well.
Okay.
Of course, if you don't have microphone set up, you can just type the question and we'll try to be looking, me and Samuel, at this question and ask it, but we really prefer if you would ask this yourself. Konstantin, go ahead.
Okay. Yeah, and please, if the person doesn't respond, read the question for me. Okay. Sorry. So let's start sharing the screen. You can see it, right?
Yes.
Okay, perfect. Right. So today I'm going to talk about proximal and federated random reshuffling, which is my joint work with Ahmed Khaled and Peter Tarek. And the talk will be organized in a few parts. So I will start with introducing you to the concept of centralized and federated learning, which are both approaches to distributed optimization. Then I will talk about Localgd in particular, which is also known as federated averaging. And I will talk about our algorithm somewhere around Localgd, and I will try to explain what we are doing based on simpler comparison beyond distributed optimization. But then I will also explain how our theory applies to distributed optimization, federated learning, and explain this through the lens of proximal operator. And this will be combined with some theoretical and numerical results, which will be closer to the end of the talk. So the first part is really an introduction. And I will start with the centralized learning. So here we have two entities. One entity is the server, something that we own and we want to use it to perform distributed learning. And we also have a number of clients or devices. I will mainly use devices for them, which can be something like mobile phones, which is the simplest example, or they can be some simpler things like refrigerators if they have some compute, or maybe it is large entities such as banks or healthcare providers who have one feature. They all have their local data. And the way centralized learning is usually done is that each device sends its local data to the server, and then the server performs the training. So the cloud gets all the data from all the users, and it does some kind of training. Maybe this is stochastic gradient descent, SGD, or something else. The main point is the server collects the data and produces a model. Then the model gets distributed to each of the devices, and the devices can now use this model. And the ultimate goal for each device to have a good model. Now, of course, this is a very precise approach. We can take all the data and solve the problem. We can solve it exactly, and that will be very good, except for one aspect. The data will be stored on the cloud. And what we actually want to avoid is to ever communicate the data to anyone from the device. So this is where federated learning comes. And our approach would be here to always keep the data private, never to share it with the server, but we will still allow for some communication with the server. So it's not completely prohibited. And the way it will be done is as follows. So each of these devices will start certain computation procedure, which I will describe a bit later, called local SGD or federated averaging. These are the same things for our intents and purposes. So they start their local iterations, they do certain amount of computation, they produce their own small models, which are based only on their local data, and then they send the obtained models to the server. The model can be something like a neural network, it can be something like a language model that tries to predict the next word on a keyboard, or it can be something simple like a linear model. It really depends on the user. So for our goals, this is model agnostic. We do not formulate explicitly what kind of model it is. So after they send their models to the server, what happens is the server uses their models to produce its own global model, which will be sent again to each of the devices. And normally this global model will be just the average of all local models. And you can read a lot about federated learning, its applications, and all of its aspects in a recent survey paper, which is just 1 year old, by Peter Kairos et al. And it goes over several aspects, such as how we can apply this in practice, what kind of differences between the applications we have, what kind of models, what kind of data it can be, how it can be applied to train something for mobile phones, how it can be used for fraud detection if banks want to identify good approaches together without sharing the data of their clients. It can be something related to healthcare and the data of the patients. And this paper, it also discusses a lot of other aspects such as privacy, how exactly we avoid revealing the data completely, how we can mitigate the issue of adversarial clients. And another aspect that is covered there is optimization. And this is actually the main topic of our presentation and of my talk. I will focus on how we can optimize a model. And I will not discuss the other issues, although I encourage you to read about them in the related literature. So seems that there is no question so far. So I will go to more technical details now. I will describe the problem. So we start with a simple finite sum optimization. And we have a sum of functions, and each function is the data of a device. It's the log likelihood or the loss associated with the local data of client number M. And we average these losses over all devices, and the total number of devices throughout the talk will be denoted by M capital. And we want to formalize that each client has its own data. So we say that each client has its own local objective, Fm. And this local objective is another sum. So this might not be exactly trivial right away, but imagine that the device or the client has a certain amount of local data, and we just apply the loss function to each data sample individually. So F capital M is also a sum of functions, and each of these functions is related to the local data. We are also going to have some more. So there is a question, by the way, in the chat, which is N capital is equal to M capital. And I will answer this in a couple of slides, but in short, no, and you'll see the difference. So now let me skip the dimension part. It's pretty easy. But now we have N capital, which is the total amount of data. And we have also local amounts of data. So the question was by Edward, if N capital is equal to M capital. And thus the answer is no, because N capital relates to all data while M capital relates to how this data partitioned into several small pieces based on clients. And a very simple relation is that N capital is equal to N1 plus N2, etc., plus NM capital. So this just means that N capital is the total amount of data. And the reason we write the objective this way, with normalizing the left-hand side by N capital, is that we actually care about the minimization of the total sum, in which each of these terms appears exactly once, and their number will be exactly N capital. So that's just for our convenience. And actually two assumptions that will be related to our theory is that the objective functions, each of the local functions in each of the sum, is strongly convex, mu strongly convex, and L smooth. So what does it mean? If the function is twice differentiable, it means that its Hessian, which is a matrix of shape d by d, that this matrix is positive semi-definite and actually is lower bounded by mu times identity. And it's also upper bounded by L. So in other words, all of its eigenvalues are in the range from mu to L, and mu here is strictly larger than 0. So this is really the problem that we consider, and I will go back to this reformulation a couple of times to remind you about this, but I hope it's clear right now. So there is another question, maybe someone reads it. Let's unmute the speaker.
Why is FMJ and not FM? Why do you have FMJ and not FM?
Okay, so the question is related to these terms inside the sum, and the question is, why do they have two indices instead of one? And the answer is,
but I think it's about below, so in the assumption of the eigenvalues.
Oh yeah, maybe yeah, below. Okay, so the answer is, it just makes the analysis much simpler. Another answer is that when it comes to random reshuffling, which I will introduce later, the theory so far requires that each function is satisfies these assumptions. So this is related to what we prove later in the talk and what is in the paper. Lifting these assumptions would be, of course, very nice, but it's just beyond the scope of our presentation. Our main goal is to introduce a new algorithm and not focus too much on the different theoretical aspects. Okay, so since no other questions so far, I'll take a pause. All right, let's go further. Now I want to talk about Localgd. So this is one of the previous slides that I showed to you, where I mentioned how the clients in federated learning keep their data private and do some local computation. Now we are going to describe exactly what happens there on the devices. So each time it's going to start with some initialization. So each client gets a model, and this model is the same for every client. Now they take this model and start using it on their local data, and the model is denoted as xt0, which is to say that we have round t. So we have had t communication rounds, and now this is a new one, and we start with this particular vector in RD. And if we take a look at the first client, what's going to happen is we first apply a single SGD step. So we take the model that the client obtained from the server, which is xt0, and then we take a stochastic gradient step with step size gamma and stochastic gradient gt1, 0. So here t relates to the round number t, 1 relates to the client number 1, and 0 from to the fact that we evaluate the gradient at xt0. And the assumption of Localgd would be that this gradient is unbiased, but it's unbiased only with respect to the local data. So we have local function f1, which is related to client number 1, and the stochastic gradient is unbiased with respect to this function only. And this is the assumption of Localgd. And then we do the same for each of the clients, for client number 2, and so on until client number m. Each of them takes a stochastic gradient with respect to its own local data and computes the new iterate. Now we can proceed in the same fashion, but now we will go from xt1i for client number 1. So it will take the previous computed model, and it will update it again with the same step size, but the gradient is now evaluated at xt1i. So without any communication, each client proceeds locally with its own local data and computes many stochastic gradients and performs stochastic gradient steps. This process is repeated for a number of steps, which I do not here as small n, and it doesn't matter that much right now. But what's important is that each client, without any communication, computes its own new local model using only stochastic gradient steps. So now this is pretty important for understanding my talk. So if there is any question about the procedure here, which I know is a little bit complicated, it would be nice if anyone who has questions asks them. Okay, so it seems so far it is clear. Do not hesitate to ask your questions, and I will go forward. So after each client computes its new local model, what we do, we send this model to the server. Perhaps in some certain differentially private scenarios, there will be some more modifications to the update, such as some compression, maybe some noise addition. We do not take this into account here for the sake of developing optimization algorithms. And after each client sends a model, these models are averaged on the server, and the process is repeated again. So the server will send the produced model, the average, to the devices, and the devices will continue computation. Now, we want to change one little piece in this algorithm, a single place that will be different. In Localgd, we assume that the gradients are unbiased. And for that, we can sample from the whole data set that is available to the client. It will sample uniformly, for example, one of the functions in its own sum. But this process is known to be, in certain situations, to be suboptimal. And how exactly suboptimal? So recall that the objective is the sum of a finite number of functions. So, and what we actually want to do, ideally, we want to approximate the full gradient of this function. So this is the loss function of client number m, and this client would ideally perform a full gradient step with respect to the whole sum. But for the sake of saving time and efficiency, the client would rather use a stochastic gradient because it's just cheaper, faster, and more efficient. However, we can be smart here. We can do something better than just sampling uniformly. In particular, in federated random reshuffling, which is abbreviated as FedRR, we do the following. We perform the same step. Again, we just take a stochastic gradient, but now the gradient is not unbiased. Its expectation is not equal to the full gradient on the previous point. Instead, you can see here in the expression below that we actually take function fmi, which means that this function is the ith function in this finite sum for the device number m. And we only use each function once. So we just take the data set and proceed first, second, third, and so on until we reach the last function, the function number n capital sub m. So we will go over the data set exactly once. And this is the modification that we propose here. And one can, of course, ask why exactly this modification? What's so good about going over the data in some random order. Why is that beneficial? And to understand this, it's best to go to the setting where we have m capital is equal to 1. So at the top, you see the objective that I formulated before. Again, everything here is finite sums, and we have many devices involved. What if there is just one device? Would random reshuffling be better in that case? So this is the answer is yes, it is going to be better, and here is why. So I will now simplify this to I will drop one of the indices because there is just one function, m capital is equal to 1. So I will simplify everything to just f small sub I. And again, we'll assume that each function is strongly convex and L smooth, for which the an equivalent formulation when it is twice differentiable, that the Hessian is lower bounded and upper bound. So for this problem of minimizing just a single finite sum, we can do either SGD, just as I mentioned before, we sample uniformly one of the functions. The next thing that we can do, we can proceed in epochs. So we have epoch T, and we go over the dataset, first function, second function, and so on. So at iteration I plus 1, we would compute the gradient of function f I plus 1. And this procedure is known as incremental gradient, and it has certain pros and cons, and that's actually the algorithm that is quite often used in practice. But what's even better than incremental gradient is random reshuffling and shuffle once procedures. So what do they do? Just as I mentioned, we would take the data that is available to us, the finite sum, and we would proceed with stochastic gradient steps by taking each function only once. And if every time we get a new permutation, a new order in which we go over the functions, in that case, we call this procedure random reshuffling, because we reshuffle after we finish the full pass over the data. If we only sample one permutation just once, then this procedure is called shuffle once or single shuffle. And it's going to have exactly the same properties. So the convergence statements are going to be exactly the same. And you can associate these two algorithms with each other because they really have almost exactly the same properties. So this is one more important slide. And let me summarize. And if you have any questions, please ask them. So to summarize, SGD would sample uniformly from all data, and it might repeat its choice. It might take the first function several times before it goes to another function. And it might even avoid sampling some functions for a lot of time because it always samples uniformly, forgetting the past. Incremental gradient goes over the data in a fixed order predefined for you. And this order might be good, bad, we don't know. It's completely arbitrary. And in random reshuffling and shuffle once, we choose the permutation, we choose the order to go over the dataset randomly. So it seems that there is no question in the chat. If so, I'll go next. Okay. Now we proceed to the part where we discuss the theory of these methods. And let me mention that the unbiasedness property of SGD is very useful for analyzing its performance. It makes life much easier. And this is why for many years, there was a huge gap in understanding these algorithms. So recently, in 2019 and 2020, there were several papers, including one paper by me, Ahmed, and Peter on the convergence of random reshuffling. And for SGD, the theory would be very simple. It would be to say that for the settings that I specified, strongly convex and smooth functions, the convergence rate is 1 over t. The nice thing is that it is completely independent of n. The number of functions does not matter. The iterates xt converge to x star pretty quickly. It's just 1 over the total number of performed iterations of the sampled gradients. And you can find the corresponding proofs, for example, in the papers that is mentioned here by Gower et al. For random reshuffling and shuffle once, the situation is quite different. The difference is that now we have 1 over t squared rate. And clearly, if the number of iterations is huge, something like 10,000, then 1 over t would be much worse than 1 over t squared. On the other hand, this is epoch convergence. So even though n here appears in the denominator, each permutation costs n stochastic gradients, where n is the total number of functions. So it means that we need to spend more effort to actually get closer to the X-star, to the solution, of the problem. You need to spend more iterations if t is quite small. It might turn out that this algorithm is actually worse for a certain range of accuracies, and this can be even proved, for which you can find some papers in the literature. So the short message would be random reshuffling has much better asymptotic rate, but because its convergence is measured in epochs rather than stochastic iterations, it can be slower than SGD for certain regimes where you don't need a high precision solution. And the next slide will be about how we generalize from m is equal to 1, m capital is equal to 1, to the general case where we have distributed setting. So everything I mentioned about convergence of SGD and random reshuffling is for the special case m capital is equal to 1. The next step would be for us to understand what happens when we go to general M. And to do that, we are going to take an unusual approach. So what we are going to do, we are going to introduce a new vector, bold X, which is just a concatenation of the existing vectors into multiple blocks. So we had m capital functions, and for each function, for each m, I'm going to define its own vector, xm, of the same dimension as in the initial problem. But now it's going to be a block of a huge vector, which is called extended vector. And to avoid conversion to something different than my solution, I need a regularizer. So here you can imagine that there is no psi at all. So we just minimize the sum. And then each function would have its own variable, and clearly the functions wouldn't know about the existence of each other. The way they know that they are connected somehow, the way we make this reformulation equivalent to the previous problem.
It's raising hand, so let me, okay, yeah. So that is Hussein.
So just to finish, the way we make sure this is equivalent to the previous problem, we put this regularizer.
Yes, hi Konstantin, hi all. Okay. So just in the previous slide, in the complexity that you showed in the previous slide. Yes, so n is in the denominator or in the numerator?
It is in the denominator, but the iterates here are the epoch iterates. So after finishing n epochs, each of which takes n iterations, I would have here n in the denominator. If I measure the complexity in terms of the stochastic gradients, n would be in the numerator.
Yeah, so because, okay, like in your finite sum, you can add as much zeros as you want, right?
Yes.
Like you're minimizing, okay, assume that you have only one function that you can add maybe 1,000 zeros, then
well,
you
actually, from the theoretical perspective, you cannot do this for the following reason. We assume that each function is strongly convex and smooth, so it has to contain some information.
Okay. Okay, so we don't have such stuff for convex.
And again, if I measure the performance in terms of stochastic gradients, not in terms of epochs, then it would be n divided by t squared. So t here, t is equal to k times n, where is k over n, where k would be the total number of stochastic gradients, because t is the number of epochs, and each epoch takes n stochastic gradients. So if I compute the number of full stochastic gradients, it would be t times n. And this is why if you introduce extra zero functions, the complexity will be actually worse, not better.
Okay, I see. Thank you.
Okay. But that's a very good question. Otherwise, it would not make any sense, this bound. All right. So let's go back to the reformulation. And again, we use the so-called product trick, which is not our invention, by the way, it's known in the literature. We use it to put an individual iterate inside each function and then connect them using the regularization function psi of x. And now this problem is easier in some sense because the functions are independent of each other, but it's also more complicated because we have constraints. These blocks have to be equal to each other. And in order to proceed to develop an algorithm, we need to understand how we can tackle the function psi of x. And the way we are going to do this is by using proximal operator. Sorry, okay, I guess I have a bad order of slides. Sorry about this. So the prox function here, the prox operator that we are going to define is just a solution of some subproblem. And it might not be obvious why we want to solve another problem, another subroutine inside our algorithm. The short answer is that for projections, it's very easy. For constraints, when psi is an indicator function, as we defined before, which is just 0 or plus infinity, the proximal operator is just the projection operator. And to project onto the constraints that all blocks are equal to each other means just to average them. So if I take any vector x, bold x in the lifted space, the proximal operator with respect to this vector x is just a stacked vector of means. So we take each block, consider this as a bunch of vectors, average them, and then we repeat this block everywhere to obtain the proximal operator. This means that to compute the proximal operator, we don't need to do almost anything. We just average the vectors. Now, how do we develop algorithms that use proximal operator? It's very easy. For example, for SGD, you would just take proximal operator after each stochastic gradient step. So we perform a uniform sampling of the functions, take a gradient step, and then apply proximal operator. And that's pretty straightforward to show that, for example, in our setting with strongly convex and smooth functions, it converges just with the same speed as SGD. So the extra function psi here does not hurt at all. We just need to evaluate prox operators. And if you translate this to the function psi, which I presented before, which puts constraints, it would be to take a stochastic gradient step to one of the functions sampled uniformly on each device, and then to average the results. So if you apply prox SGD to the reformulations that I introduced, you can verify, it might not be obvious right now, but it can be verified that the procedure will be just standard synchronous SGD. You take stochastic gradient steps, you average the results. Now, one can think that for proximal random reshuffling, which we want to do here, the algorithm would be just the same, very easy. You apply prox after each gradient step with respect to a gradient inside the permutation. And that turns out to be a bad idea. Now, the intuition why it is a bad idea is that we want to actually perform a lot of gradient steps. We would like to compute xti plus 1 using just stochastic gradient from the permutation. And only after you perform each of these stochastic gradients, after you go over the whole data set, you get xtn. And only to xtn you apply the proximal operator with a larger step size, with step size gamma n. So the intuition here is that because we take each gradient exactly once, this would be very similar under small step size gamma to a full gradient step with a larger step size equal to gamma n. And the reason behind this is just xtn is equal to xt minus gamma times sum of gradients. And because our objective f is normalized by n, and we don't normalize gamma by n when we run random reshuffling, because of this, the step size gets larger. and we need to take a larger proximal step. So this is how one should take, how one should generalize random reshuffling to the proximal setting. And another example where it's very easy to see that this is the right change is when each function is just linear, because its gradient is going to be equal just to ci independently of x. We are going to see that for xt plus 1 defined here, the defined procedure will generate exactly full gradient step with larger step size. So this is really the procedure that we want to do, and not the procedure where we apply proximal operator after each iteration. And if you now try to understand how fast it converges, so this is going to be pretty simple. We are going to have linear convergence up to some neighborhood. So you can see in the bound here, x star would be the solution of our problem. 1 plus gamma mu n is the contraction that we have here, because it is with power -1. So the factor in front of x0 minus x star norm squared, this factor is smaller than 1, and it decreases exponentially. And it decreases exponentially just as fast as we would expect, except that there is also another term, which is gamma squared sigma rad. And what is sigma rad? It's very easy to upper bound this constant with other things that we know. So normally, the convergence of prox SGD would be also very similar. It would be linear rate of convergence plus some noisy term, with the difference that it wouldn't be sigma rad squared as we have here in the bound. It would be sigma star squared, which I defined below, which is the variance of all stochastic gradients at the optimum. And why do I say the variance? Because the full gradient at the optimum at point x star is just nabla f of x star. And if each function is stochastic, then nabla fi of x star is a stochastic gradient, and we just compute the empirical variance at that particular point. The nice thing is that this constant is always finite. It's very likely to be larger than 0 unless each stochastic gradient is equal to the full gradient. And it allows us, the sigma star squared, it allows us to upper bound sigma rad squared just the way we would expect. So if there is no nabla f of x star in the expression for sigma rad, then this expression is just the same convergence rate as we have for random reshuffling. And for example, when we have a distributed setting and the data is IED, this corresponds to nabla f of x star being equal to 0. And in that case, with IED data, when the devices have the same objective functions, but they probably go in different orders, so there is some benefit of averaging the results, we just recover the rate of random reshuffling. And if you go to the settings that I described before, and where I compared random reshuffling to SGD when m capital is equal to 1, this is going to be the same rate. So we know that this theory is tight at least in one case. Now, this term here, nabla f of x star, you can show that it's actually equal in the distributed setting to the sum of gradient norms of the local gradient squared. And that means the following. So I want to minimize the sum of functions, f capitals, and each function might have the same, so all functions might have the same optimum, in which case this expression is just equal to 0, because the gradients will be equal to 0 at the same point, x star. This means that they have the same optimum. But if this quantity is larger than 0, then we just know that this measures how different the local data sets are for each of the clients. And because here we have gamma squared in the top bound, this means that we will get just the same rate 1 over t squared as before. So are there any questions about the rates that we get here?
So I have a mock question. So in the neighborhood, so you talk about the sigma rats. How about the dependence on gamma? Can you comment on that?
Yeah, so for random reshuffling, for the bounds that we have here, the dependence is gamma squared, while for SGD, it will be gamma without any square. This means that if I want to converge to epsilon precision, so I want this upper bound to be smaller than epsilon, what kind of t and what kind of gamma should I choose? Gamma should be something like square root of epsilon for random reshuffling, because we have gamma squared here. So to make it smaller than epsilon, we would need gamma proportional to square root of epsilon. For SGD, to make gamma sigma squared smaller than epsilon, we would need gamma be proportional to epsilon. So these are different orders of magnitude. If epsilon is something like 10 to the minus 8, then I can choose 10 to the 4 times larger step size for random reshuffling. And because it can converge with larger step sizes, it converges actually much faster than SGD. And the dependence on the number of stochastic gradients is better asymptotically. So does that answer your question?
Yes, perfectly. Any other questions? Anyone?
All right. Then I guess we can describe the experiments. So here is a very simple experiment with logistic regression. And to make the functions strongly convex, we use L2 regularization, and logistic loss is always smooth. So if you take the cross entropy, everything is satisfied, all assumptions hold. And now let's run federated random reshuffling, which we introduced, which goes over the data in random order, and use Localgd. So here I compare federated random reshuffling, which goes over the whole data set, to two variants of Localgd. In one variant, which is the blue line, I compare to the variant of SGD, which also uses the number of stochastic samples per iteration, just the same as federated random reshuffling. So if I have 100 samples and I split them into 10 workers, each worker gets 10 samples. So that means that federated random reshuffling would perform 10 local steps. And here for Localgd, I would use the same number of local steps to compare to make the comparison to federated reshuffling fair. And you can see that there is also the orange line, which has 5 times fewer local steps. And this approach for Localgd performs even better than Localgd with full number of passes. Because what happens with SGD is that the local models, they pretty quickly diverge from each other unless the step size is very small. And because random reshuffling can benefit from larger step sizes, as I mentioned before, it gets a huge advantage at the beginning and converges much faster in terms of the communication number.
You have a question?
Okay.
Konstantin, you're unmuted.
Okay. Thank you, sir. My question was about the previous slide.
Okay.
So you showed the L2 convergence of the iterate, yes, and the sigma had depend on n. So
yes.
n here is the total number of data point, right?
Local data point for yeah. So this bound is written specifically for proximal setting, but if you translate this for distributed optimization, yes, it would be the number of local data points.
So and is it going to have an impact if we have like large scale data set where the number of data points is really big?
Yeah. So just as with random reshuffling and SGD, random reshuffling is going to become eventually better than SGD. And depending on the number of functions, and this might happen fast or pretty slowly if it's really huge. So we can actually even see it in numerical comparisons that random reshuffling for small number of epochs is worse than SGD when n is small. So for large scale data sets, you would need at least 100 passes over the data to beat SGD, something like that, or maybe 50, but then it will become better and better compared to SGD. Here we have also similar dependence on n, except that there is this thing with the gradient norm, which does not appear in the bound for SGD. And you can see, so probably I will go here just because this expression for sigma rat is easier to see. You can see that there is an extra term n in front of the gradient norm here, gradient norm at the optimum. So depending on which term dominates in this bound, the gradient or the variance, random reshuffling can be actually much worse for large-scale data sets. And this is something that, again, can be checked numerically, that it would be worse in certain situations. That being said, I would probably add that, for example, for training neural networks, random reshuffling is the algorithm to go. So if you look up, for example, the PyTorch tutorial for training convolutional neural networks, you will see that the data loader there uses random reshuffling. It's called SGD in PyTorch and other programming languages, but the actual algorithm that is used due to how the data is sampled is random reshuffling. So it actually, in most cases, performs better than SGD because even for not so crazy precision values such as 10 to the -4 accuracy of the final solution, random reshuffling already becomes better. And not to mention that neural networks and similar applications are large scale. So I guess this answers the question.
There's no more questions at the moment. Oh, there's one by Yegor. Let us unmute Yegor. Okay.
Hello, Konstantin.
Hey.
I just wanted to ask whether you investigated how heterogeneity affects the performance of like federated random reshuffling.
So do you mean numerically or theoretically?
Theoretically.
Okay, so we do have bounds for non-ID data in the paper. I did not include it here except for this expression, like what exactly that would be. Essentially, you have this extra term. So this would be the gradient of the local data set, right, of the local function. It's not the variance, like it's not the variance compared to the whole sum. And in that case, when there is a regularizer, this bound can be even not comparable directly to the bound of local SGD. However, if you just have non-ID data and the non-IDness is not crazy, this bound is still going to be better eventually, because the asymptotic rate 1/t² is ultimately going to beat the rate of SGD anyway. At the same time, there are similar constants that appear in the bounds for local SGD. What is worse in local SGD is the step sizes that it needs to take. So for non-ID data, local SGD needs to decrease the step size as 1 over the number of local steps. And this is why it performs slowly in practice when you actually use small step sizes. Here, our theory works with just standard step size 1 over L. And this is a huge advantage over local SGD. So this advantage would be particularly big when there is a lot of local data, because local SGD with many local steps, as I showed in the experiments, it doesn't perform well. And if you look up, for example, papers on local SGD and how they scale with the number of local steps, it pretty quickly becomes very bad. So you wouldn't do like 100 local steps for local SGD. It's better to use a modest number. Here, you can actually perform the full pass over the data. It does not hurt the step size. Okay, so I guess the question by Yegor is answered. And
yeah, there is one question from Edward. I'll try to unmute him.
Okay.
Okay. Hello. Can you hear me?
Yeah.
So my question was very close to what you just discussed. I'm just wondering about how to choose number of local steps. So in theory, as far as I get, it should be the same as the number of as the size of the local data set. Am I right?
Yes, and to clarify, each function, each device might have different number of local functions. It's completely okay.
Yeah.
So you just finish the pass over the whole local data set. That's the important part.
Okay, and in the experiments, do you use the same permutation so do you continue the pass through the permutation in, let's say, two neighboring local rounds of local SGD? I mean, for example, when the size of the local data is much bigger than the size, then the length of the local loop, do you use the same permutation during the neighboring local loops?
So if I understand correctly, your question is about local SGD and how I run it when the number of local steps is large.
It's about federated random reshuffling.
Okay.
So in the experiments, you say that you take the same number of local steps for local SGD and federated random reshuffling.
Yes.
Okay. And so do you use the same permutation? Do you continue the pass through the permutation in two neighboring local loops of federated?
So for federated random reshuffling, I just finish the local loop and then it communicates and restarts the loop. So each function is visited exactly once. For local SGD, it would be sample many times and have equivalent number of stochastic gradients before communication as for federated reshuffling. So the number of local steps here is defined by the number of local functions to run federated RR.
Okay, so number of local steps in local SGD is the same as number. Okay.
Yes, for the blue line. And for the orange line, it's 5 times smaller.
Okay.
And one of the points here is local SGD with fewer local steps performs better than local SGD with equivalent number as for federated random reshuffling steps.
Yeah.
And that's because local SGD does not scale well with the number of local steps.
Yeah, makes sense. Thank you.
Thank you for the question.
So I have a question, if I may. Are the permutations on different machines synchronized or are they independent?
They are independent. So each device samples the permutation independently of all the other devices. So they do not really care about each other. And the theory works the following way. We need a random permutation, but the way you define the local function implies that because the functions are equivalent to each other, it means that each of the devices can just decide on its own what kind of permutation it should use.
Thank you. I don't see more questions. Feel free to continue with the plots.
All right, that's actually the end of my talk, and I just want to mention a few more things that you can find in the paper, which just did not fit this talk, because we did other things such as certain adaptive step sizes, like how you can make sure that each function is having the same weight as others when the step size depends on the function. We also characterize how you should decrease the step size, how you can generalize federated RR to a proximal operator with some other non-smooth function like L1 regularization, and explicit upper bounds for IID and non-IID data are also there, with the discussion of how they affect the convergence rates.
Okay, very good. Thanks a lot for the talk. So let us open the floor to questions. Samuel, could you allow everybody to unmute themselves so that people can ask questions at will?
So yeah, if you have a question now, like feel free to unmute yourself and ask the question.
Hello.
Hey.
So one thing that I would, so for example, if you add like variance reduction techniques on it and remove the neighborhood, so will it still be better the standard variance reduction techniques? I mean,
No, I mean variance reduction in that sense. I'm not sure how exactly you would perform variance reduction, but if you take into account the data heterogeneity as well as variance of the stochastic samples, then you can actually achieve an even better rate. It would have several disadvantages, such as you would need to compute full gradients, you would need to store extra vectors for their computation, and also you would need to make sure that the gradient differences still make sense, which is hard to achieve, for example, when training neural networks.
Yeah, I mean, but the rate is better because of the neighborhood, because of the gamma square that
you would beat the neighborhood, yes.
Yeah, I mean, once you add this variance reduction technique, it seems like you lost the advantage. You get the same linear rate as without random shuffling, if you can actually do the variance reduction.
Yeah, if you can, you can get a better rate. Yeah. Okay. Another thing to mention here, it might be in certain cases to also do variance reduction with reshuffling. So the standard variance reduction just samples uniformly, but this has disadvantages. For example, when you use small data sets, it actually doesn't matter small or not. So when you have continuous places in the memory, when the dataset is loaded in the memory, random reshuffling just goes over the permuted dataset, and it's much faster to load the data than to sample uniformly, because you would have cache misses when you doing uniform sampling.
Yeah, but you also need some time to reshuffle it, right? If the data is large, then reshuffling also might be
not really, because you can just shuffle once.
Oh, you mean once?
So here I describe RR because it's a little bit more recognized in the literature, but the bound would be actually exactly the same if you just shuffle once the data at the very beginning and then go in the same order.
Okay, thanks.
Any more questions? Remember, you can.
Hello, Konstantin. Thank you very much for such nice talk and very precise description, even up to scalars. So yeah, very nice talk. Thank you very much. I have two questions. So I didn't get. So is after each communication round permutation is different? And second question, what do you think? Is it possible to, if you consider permutation and select uniformly permutation from the set of all possible permutation, is it possible to sample permutation in some principle to improve bounds even more?
The second question is particularly nice because I don't know. It would be very nice to know if we can find some good permutations, but except for one recent paper that appeared on arXiv maybe just 2 weeks ago, there is little understanding about how to sample permutations. And the message in that recent paper is that for general functions, it's not possible to improve the rate. So the rate cannot be improved. There is a lower bound. You cannot improve just by sampling a permutation with some nice idea. At the same time, in our paper, in our new RIPS paper about just random reshuffling, we show that sometimes a good permutation can make convergence 100 or 1,000 times faster, but it just no one knows how exactly to get those good permutations. Your first question was how we sample permutations. Do we resample the permutation after each communication round? So the answer is it's up to you. Actually, the rates will apply to both situations. If you do not resample the permutation, you will still get the same convergence rate, at least in the strongly convex and smooth case. And in practice, that would be probably much better to just keep the permutations the same.
Okay, thank you.
So I have one question. Are you aware of any paper in the literature which combines random reshuffling and proximal steps outside even of federated learning setting or distributed setting and so on?
No, as far as I know, proximal operator for random reshuffling was not existent. Simply because I think it's actually not trivial to me how to show that it works if you apply prox after each step. It's not clear to me if it would converge in general, if it's a good method. It seems that the answer is no. At the same time, that's the most intuitive approach. Just take prox SGD and generalize to prox random reshuffling by changing the way gradients are sampled. And this is, for example, how it's implemented in many GitHub repositories that I found. I never found a repository that would have the same procedure as ours. And I think that's the reason people didn't know how, if somebody tried, why they wouldn't be able to show that it works.
Sorry, any more questions? Remember, you can unmute yourself just in the same way I just did for myself. So while people are thinking, another question. Do you think it would be possible to take multiple passes over the local data before taking a prox? What would you think would happen?
I think the answer is pretty simple, and it would be just that here in this upper bound. So my answer would be, I think it is possible, and the change would be the rate will be becoming worse and worse in that terms that includes the norm of the gradient squared, because this term is the price we pay for not using the proximal operator after each step. So for example, if we have just the same functions, if all functions are just the same function, then our algorithm would reduce to gradient descent, proximal gradient descent, with steps taken, with proximal steps taken only every few iterations. And I think this is the reason we have this term that is in the frame on the slide. And I think this term would be getting worse and worse if you increase the number of passes without computing the proximal operator.
Thank you.
Yeah. So Konstantin, maybe like another question. What do you think here about adding mini batching? So instead of taking like every single point, maybe if you combine few, can it help? Can it actually bring, like, can you actually find like the, let's say, optimal batch size for this approach?
So I think that, what do you mean optimal batch size?
Like the with respect to the convergence rate.
I think that just as with local SGD, your rate doesn't improve with increasing batch size. You just can use parallelization, and this is why mini batch version is good. But I don't think that the rate itself, even for a local SGD, improves if you take into account the total number of stochastic gradients. So here, I'm not sure how exactly the rate will change. Probably this gradient norm term would be getting better much faster than sigma star, because you can see that n appears essentially as n squared in front of the frame term, in front of the gradient norm. It's n outside of the parentheses, and 1n is also inside. So this term, if I have mini batch size B, this would be probably n divided by B, because I would need fewer gradients to finish the pass over the data when I do mini batching. The other term, sigma star, I think it will just, by standard laws of variance reduction, it would get divided by B. So one term would improve faster than the other. And to some extent, probably you can get a better rate. I mean, if you ignore the issue of computing more gradients per iteration.
But for instance, like also Lmax can decrease, right?
Yeah, you probably can replace Lmax with some smaller constant if you use mini batches. Yeah, that's a good point.
I have one more question. So, so it is known that local gradient descent, let's simplify, local gradient descent or local SGD doesn't improve in communication complexity when compared to non-local gradient descent in the heterogeneous data regime. So you need some level of data homogeneity for some improvements to kick in. Now, how would you, so let's say we're in the heterogeneous data regime and you want to run and compare FedRR with local, let's say, gradient descent.
Mm-hmm.
How would that comparison go?
So random reshuffling is better than gradient descent, just without any distributed setting. Random reshuffling is better than gradient descent only until up to some accuracy, until when the required precision is some small number like machine precision. It might eventually become better to use gradient descent with full gradients. Now, when we compare the bounds for FedRR to just local gradient descent, I think the bounds for local RR are significantly better, because you can actually recover a bound for local gradient descent from this one just by assuming that for each function, for each local function, f capital M, it is a finite sum of its copies. So it would be taking the gradients of the same function at each iteration locally. So and you would get a bound for local gradient descent. And I think this bound would be also better only if you perform a lot of steps, because sigma star in that bound would disappear. But for this to kick in, I think you need a lot of a very high precision solution.
So are you saying that this is the first local type method which beats standard gradient descent in the heterogeneous setting as a benchmark, which on its own beats all local gradient methods in the heterogeneous data setting?
So yes, in certain accuracy regimes, like in certain ranges of target accuracy, the answer is yes.